Hey, Michelle Glass here. Welcome back to another episode in Chapter 26. Our job for this video is to look at the glomerular capsule in more detail. This is, of course, the beginning of our nephron. This is where filtration takes place. So this is the process how we initially get material out of the blood so that we can turn it into urine. Taking a look here, we can see that the glomerular capsule is composed of simple squamous epithelium. We have a layer of cells on the outside of the capsule, and then we have a layer of cells actually surrounding the glomerulus, which is the capillary network that's extending into the capsule. Notice too, you have a capsular space. So as we pull things out of the bloodstream, it's going to be filling up that space. Notice that your afferent arteriole is going to be the entry for the glomerulus capillary bed. The afferent arteriole has a larger diameter than the efferent arteriole, which is your exit point. This is going to be important because since you are allowing a big opening and then a small exit, you're building up pressure inside that glomerulus. So the glomerular blood pressure is higher than the systemic blood pressure. And so this is going to make the kidney very sensitive to the blood pressure in the body. You have a group of endocrine cells embedded in between the afferent and the efferent arteriole. These cells are referred to as the juxtaglomerular cells. We've seen this prefix juxta before. It means close to. So these cells are close to that glomerulus, which is that capillary bed. These cells are going to be sensitive to changes in blood pressure as that blood is flowing through the glomerulus. And as a result, we're going to see these cells releasing renin, which we've talked about before, and we're going to talk about again, and also EPO, which we've talked about before. Remember, that stands for erythropoietin. Let's take a look at those cells that are surrounding that glomerulus. Those cells are going to be, of course, part of the glomerular capsule. They are called podocytes because they have these special little extensions of the cell that look kind of like feet, or they're described as feet, that wrap around the capillary, and then they form these little filtration slits. So as we are pushing material out of the glomerulus, that material has to fit through these filtration slits. We also have a group of cells called mesangial cells, or intraglomerular mesangial cells. These cells are going to have the ability to do some contraction. They are important in structural support. They are important in filtration. They're important in phagocytosis. But really, we're going to talk about them as being important in helping to regulate the glomerular hydrostatic pressure. Glomerular hydrostatic pressure is just a fancy way of talking about the blood pressure inside the glomerulus. We'll see that these cells are involved in autoregulation. So if the blood pressure is low, then these cells will contract, decreasing the diameter of the glomerulus, increasing the blood pressure. So this is a really quick, very localized, automatic way of helping to adjust the glomerular hydrostatic pressure. When we talk about the filtration membrane, we are looking at material moving through the fenestrated capillary of the glomerulus, through the basement membrane, and through the filtration slits of the podocyte. Filtration is basically talking about an external force, in this case that's the heart, pushing the blood through the glomerulus. And as it does that, anything that can exit will exit. These are fenestrated capillaries, so that means pretty large stuff, water and ions and nutrients can all make their way into that filtrate, the filtrate being the fluid that's getting pushed out of the glomerulus. So we're going to see initially that a high glomerular hydrostatic pressure, which is the blood pressure coming from the heart, moving through this large afferent arteriole and then being squeezed out of this tiny efferent exit, we will see that it's this pressure that is giving us the force to initially filter material out. So at the afferent end of the glomerulus, we're going to get this mass exit of water and ions and nutrients. Anything that can fit through the openings will fit through the openings and make its way into that capsular space. Now, not everything can fit through. You're going to have large plasma proteins that are stuck in the glomerulus, and they're going to stay there. As material is exiting, then you're concentrating those plasma proteins. When those plasma proteins become concentrated, we now have another pressure. This pressure is called the blood colloid osmotic pressure, and it's going to actually pull water back in. Colloid is referring to a suspension of proteins. So this is talking about the suspension of proteins, those plasma proteins that cannot exit the glomerulus. Osmotic pressure is talking about the pull of water. So because you get proteins left in the blood of the glomerulus and they're concentrated, some of that fluid that was filtered out is going to get pulled back in. So here we're looking a little bit closer at what's going on inside the glomerulus. So we've got a lot of different forces at play. We've talked about the glomerular hydrostatic pressure. It's that force coming from the heart. So as you're pumping blood through the arterial system into that afferent arteriole, you're going to see that if anything can leave through the openings of that filtration membrane, then it will leave. So you're going to get this mass exit of water and ions and nutrients, okay? But not everything is going to leave, because that capsular space already has some stuff in it. It's not empty. So because there is some material already in the capsular space, we can call that the capsular hydrostatic pressure. That's going to oppose some of that exiting from the glomerular hydrostatic pressure. So it's going to reduce some of that force that's pushing material out. So we don't have quite as much leaving as you would have if that space was completely empty. Then we've already talked about, as we progress through the capillary, you start to get this concentration of those plasma proteins, creating the blood colloid osmotic pressure, which is going to pull water back in. There's a fourth pressure that can be involved, although it's typically zero. You can have what's called the capsular colloid osmotic pressure. So if you had damage to your blood vessel and you had leakage of plasma proteins into the capsular space, that could alter the filtration that would be happening here. When we look at the net filtration pressure, it's taking into play all of these four forces together and how they interact. So we actually see that our overall filtration pressure is less than what it would be if you had just the glomerular hydrostatic pressure. So we see it's been reduced to about 10 millimeters of mercury as the average pressure causing filtration to happen, but this is still adequate to give us a good amount to filtrate into that glomerular capsular space. The glomerular filtration rate is the amount of filtrate that's produced per minute. Now this is going to be regulated in three different ways. So one way is auto-regulation. So you can adjust the afferent diameter and the efferent diameter, and you can also make adjustments with those intraglomerular mesangial cells to alter the diameter of the glomerulus. So in this case, if our blood pressure was too low, then we're going to get our afferent diameter to be bigger, our efferent diameter to be smaller, so making a lot of blood enter and then a small exit is going to build up some pressure. And then if we further constrict the diameter of the glomerulus, we're increasing our blood pressure there as well. If blood pressure is too high, then we might do the opposite of this. We also have hormones that are being produced by those juxtaglomerular cells. We're going to see here again the RAS, the renin, angiotensin 1, angiotensin 2 system. We've talked about this before, but we see it at play here specifically. Juxtaglomerular cells will produce renin when blood pressure is low. This is going to configure or activate, we could say, angiotensin 1, which can be converted in the presence of the enzyme angiotensin converting enzyme, or ACE. to angiotensin II. We know that angiotensin II has lots of different activities, including the release of the hormone aldosterone to increase sodium retention. We see it can cause peripheral vasoconstriction. We see also that the central nervous system is going to increase thirst and also trigger the release of ADH to increase water retention. So we'll come back to these and talk about them again in more specifics. If your blood pressure is too high, then you're going to get the release of natriuretic peptide, but this is coming from the heart. This is going to dilate those afferent arterioles and constrict those efferent arterioles, and then also reduce your sodium retention so that you're reducing overall your blood pressure. And then we can have some autonomic nervous system control here, specifically the sympathetic, can do vasoconstriction. So we can see this autoregulation happening right there from the glomerulus. We see hormones, which we'll be talking about again, and we can see the sympathetic division playing a role here as well. And that's it for now.